Well, so the title of today's lecture is Modular Spaces. So up to now we considered local properties of complex curves in almost complex manifolds, but for significant applications one need to study existence of either compact curves or sufficiently big holomorphic disks, as was done in the lecture of Sukhov. So let me start from the point which was the final point of the previous lecture, from the non-squeezing theorem. This general statement is the following one. One considers a ball of radius r in R to n and a cylinder of radius small r, again in R to n, and this is a product of the disk of radius r with r to n minus 2. So this disk is in coordinates x1, y1, let's say, and here are coordinates x2, y2, and so on, xn, yn. N bigger or equals than 2. Symplectic form in R to n is standard, means the sum of dxi dyi I from 1 to n. Theorem of Gromov states the following. So I repeat the formulation. If there exists a symplectic embedding phi from the ball to this cylinder, then R is less than equal, so big R is less than equal than small r. Of course, if this condition is satisfied, then the trivial embedding will work. Okay, so this is of course, necessary and sufficient condition. Symplectic embedding or symplectomorphism is a map such that it preserves a symplectic form in question. So in our case, the pre-image of the standard symplectic form should be the same thing. This is a symplectic mapping or symplectomorphism. Remark that symplectomorphism preserves the volume form. So since omega standard to the power n is nothing but a volume form of R to n, so it's a product of dxi dyi, then every symplectomorphism preserves also the volume. And this was the main thing which was used in symplectic topology up to Gromov. So somehow nothing more than follows from this volume preserving property was known, more or less. But you can easily construct a volume-preserving embedding of a ball of any radius to a cylinder of any radius. For example, you can take such a map which sends x1, y1, x2, y2, and so on to. So if you want to squeeze it, so you take epsilon x1, y1, I'm sorry, epsilon y1, and then 1 over epsilon x2, 1 over epsilon y2, the rest you don't change. This is a volume-preserving map which squeezes the large ball to a narrow cylinder. But you cannot do this symplectically. This is the meaning of this theorem. Well, so the proof was given in dimension 4. And let me, well, it's a nice theorem, so let me once more repeat the proof. So suppose you have a mapping from the ball of radius r to such cylinder. So taking ball of a little bit smaller radius, you can suppose that the image is a relatively compact domain. And if this is a 0, you mark the image point by phi of 0. Now you are in the product of the disk with this thing lives in the product of a disk with r 2n minus 2. Therefore, in fact, since it is a relatively compact thing, it belongs to the product of, so let this be u. U is phi of the ball. Therefore, u belongs, in fact, after possibly a translation, if necessary, to the product of the disk with a cube. With a cube 0a to the power 2n minus 2 for sufficiently big a. And this thing, this thing is a subset in the product of the disk with a torus of dimension 2n minus 2. Yes, you can factor r 2n minus 2 by the lattice, by this lattice. Okay? And then, in its turn, this is an open subset in the product of the sphere with a torus. And this will be our manifold X, compact manifold X. Now, we have in both ends, here and there, we have a standard symplectic form. We write this symplectic form as omega 1 plus omega 2, where omega 1 is dx1, dy1, and omega 2 is the rest, dxi times dyi, I from 1 to n. Now, we can extend omega 1 from the disk, the area of this disk with respect to our form omega 1 is pi r square. Then we can extend this form from the disk to the sphere in such a way that integral over the sphere of the extended form, which I don't change the notation, will be, well, it must be it must be bigger, but it is in our, we can make it a little bit bigger, plus epsilon. So we can extend the area form from the disk onto the sphere, adding very little as we want, but positive. So epsilon is positive, but it can be made arbitrarily small. With the second form, you don't need to do anything because it is translation invariant. So already this form exists on the torus. So omega 1 was extended to the area form on S2. Omega 2 is not changed. And the sum omega will be a symplectic form on our manifold X, because omega 1 is closed. Omega 2 is closed too. So the sum is closed and nowhere degenerate. So we got a symplectic manifold, compact symplectic manifold, and we have a symplectomorphism from the ball with the standard symplectic structure to the symplectic embedding to this symplectic manifold. The image is a open set, and then we can recall that we have here also the standard complex structure. We can push the structure forward and to get an almost complex structure, because mapping is only smooth. We can get an almost complex structure on the image, on U. Standard structure is calibrated by the standard symplectic form. Our mapping is a symplectomorphism. Therefore, the image of the standard structure will be calibrated by symplectic form in the image. By proposition 1 of my previous lecture, well, after shrinking a little bit, which I don't care about, we can extend the image, the push of our complex structure, we can extend to a calibrated, omega calibrated, almost complex structure on the whole manifold X. So we extend this thing to a compact manifold X. Now the claim for any omega calibrated almost complex structure J complex curves J complex curves cover X. Through any point of X, you can pass a J complex curve. There are a lot of J complex curves. So if you can prove this, then you are done. This was explained by Sukhov. So if I have so many curves, so I can take one of them which goes through the image of 0. Call it C. Moreover, I was not very specific here, but I can take the C to be homologous, well, to the, well, actually, it's more or less the only possibility. I can take C to be homologous to the obvious spherical homology class, to the unique spherical homology class which exists here. So homologous to the sphere times point. So in fact, J-complex spheres in this homology class already cover the whole manifold X. So I can take it, and I can write that the integral over C of my symplectic form by the homology reasons is equal to the integral over sphere times point of omega 1 of omega, and then on this horizontal thing, omega is equal to omega 1. Okay? Which is, due to our choice, is PR square plus epsilon. P small r square plus epsilon. At the same time, this integral is equal to the integral over the preimage. Let me be more precise. It's not equal, but it's bigger or equal than the same thing, integral of omega over the intersection of C with U. Yeah? U is a subdomain, C is bigger, so we take this intersection. C intersection with U. Okay. And now this integral of C over C intersection with U of omega is equal to the integral over the preimage of this curve of the standard symplectic form, because phi is a symplectomorphism. Now the preimage of this piece of curve is a piece of complex curve passing through the origin. By the mentioned theorem of Lelon, this thing is bigger or equal than P big R square. There we got that P big R square is less or equal than P small r square plus epsilon for arbitrary epsilon. Theorem is proved. Now, the point, so the main difficulty is this claim, of course. In dimension 2, as it was explained in great details by Sukhov, you can change this thing by some more or less equivalent thing, just produce the disk passing through this point using using 4 dimensions, and this is very important. In higher dimensions, such techniques is not known to work. Now, in our case, we are going to prove much less precise statement, but more general, and it will be sufficient. So we are going to prove this. We are going to prove more or less that in many cases, whatever almost complex structure is, you have a lot of J-complex curves. This is a central point of the whole theory. So you have a lot of complex curves. So now we are going to do that. point 2 moduli spaces of rational curves. Of rational curves. So we consider a symplectic manifold, compact symplectic manifold. So in particular, we suppose that this form is closed from now on. And we fix a homology class A in the second homology group of X with integer coefficients. So an example which we shall keep in mind is when X is a product of a sphere with a torus and homology class is that of sphere product with a point. We consider the Banach manifold of almost complex structures on X tamed by our symplectic form with an appropriate regularity. So C1 alpha smoothness is enough. So we can consider C1 alpha structure. So we must consider the finite smoothness because we want to have Banach manifold. We cannot consider C infinity structures, which is a Frechet manifold. And now, over this manifold, we consider the manifold of J holomorphic curves. So this is a Banach manifold of J complex curves C, which belong to the fixed homology class. So for every J, we consider all J complex. And one more thing, C are diffeomorphic to the sphere. Only spheres. Well, it's not necessary in general, but we consider only spheres. So now we have this manifold J, which is a contractible manifold. Over every point, over every structure J, we have a set. I don't say this is a manifold. We have a set of, we shall denote it by P, A, J. These are J complex spheres in A, which are homologous to A. So first claim is that PA is a Banach manifold. And the natural projection from PA to the space of structures is a Fredholm map of index. So index of this real, well, everything is real, in fact, is 2 times first Chern class of X evaluated on the homology class A plus n minus 3, where 2n is the dimension of x. So we have a manifold. So all these guys form a manifold, even if some slices are not manifolds. And the projection which sends, so P of curves over J go to J. Okay, the usual projection. Well, it is a smooth map, of course, and its differential at every point has index. So differential is Fredholm. So differential is a map from the tangent space. Is Fredholm. It means that kernel of this differential and co-kernel have finite dimension. And index of this guy is a map from the tangent space M. I will explain what is that, to the tangent space to the space of structures. So at point Cj to points J, and this is a dimension of kernel minus dimension of co-kernel. And this index is equal to this. Okay. Well, now, yes, one thing one should add here. I should explain what is this. So it is specific for spheres that these slices so defined are not compact. This is bad. Why? Because if you have a holomorphic sphere, so a mapping from P1 to our manifold, J holomorphic for some J, then for any fraction linear transformation, the composition, I write it this way, will be again J holomorphic. Again, J holomorphic. But this thing does not give us the new object. Its image is the same. Therefore, it is custom to make denote this group by G, the group of automorphism of the Riemann sphere. And then you can quotient the space of curves for every J. You take a quotient by this group, as here. And now this is a moduli space of rational curves on X omega. Rational curves meaning that they are J complex curves for some tamed almost complex structure. Well, and this factor is what we denote by MA, moduli space. So we factor out reparametrization, and we are left with a geometric object. Well, okay, so for the moment we have this. It's still not compact in general, but is much more reasonable. Now I need to explain you somehow this formula. So okay, I will not give you all details, but at least I will give you an intuitively clear reason why this formula should be true. Well, just if you have a sphere embedded into some manifold X, two-dimensional sphere, embedded manifold X, you have almost complex structure on X, and this sphere is J complex. Now, how to understand what is the dimension of the manifold of spheres? Okay, of course, every move of the sphere is a section of the normal bundle. To move a sphere, it's the same as to take, well, at least on the level when you compute parameters, it's the same as take a close to zero section of the normal bundle. And then you must write equation of holomorphicity on that. And you will got that your index, this equation will produce you that the index is a dimension of sections of the normal bundle, or sections of the normal bundle. And this is a bundle of, because we have structures here, this is a bundle of complex rank n minus 1. Minus relations, and this will be dimension of the first cohomology group on C with coefficients in this normal bundle. So somehow when you compute how many sections you have, you will go to this formula. Now, Riemann-Roch theorem tells us that this thing is equal to 2 times first Chern class of this normal bundle, evaluated, of course, on our curve C, plus rank of the bundle, which is n minus 1, times 1 minus genus of the curve. Genus is 0 in our case. Now about Chern class. So this is a Chern class of the normal bundle. The whole tangent bundle to X, when restricted to our curve C, is a, well, it's not a direct sum, but it is, it's in the exact sequence. So the tangent bundle to C is a subbundle, and the quotient is the normal bundle in question. Therefore, as I explained, as I mentioned last time, the Chern class of X evaluated on C is the sum of the Chern classes of this bundle and this bundle. So the Chern class of N, which appears there, evaluated on C, plus the Chern class of the tangent bundle, which is a Euler characteristic. So 2 times 2 minus 2g. And now I can put C1 into my formula. So I will have 2 times C1 of X on C. So this is computable things. Minus 2 times minus 2g plus n minus 1, 1 minus g. So this is 2 times C1x on C plus n minus 3 times 1 minus g. Now this is a general index formula. for curves of any genus, in fact, for complex curves of any genus. So in our case, when we work with spheres, we get our formula from the very beginning. So once more, we have now, after factorizing, we have a manifold, Banach manifold of rational curves with respect to all structures we have. This manifold projects onto the Banach manifold of structures. Projection is P. And index, this is a Fredholm map. And index is given by this relation. Now, we use a Smale-Sard theorem, well, which tells us the following. If you have a Fredholm map, and if the index of this map, is positive, then for a general J, general in the sense of category, for the set of second Baire category, for general J, pi minus 1 of J, and this is a manifold of curves. This is a space of J complex spheres. It's exactly the space of J complex spheres. So this guy is a manifold, is a smooth manifold. Manifold of dimension equal to the index. Well, in fact, one proves that in this case, differential is surjective. So cokernel has zero dimension, and index is dimension of the index is equal to the dimension of the kernel, and this is a manifold, the space of solutions. So in the case where index is positive, and this is the first part. Well, this is a theorem, but it has some addition to this. To this theorem, we can add. In the same setting, for a general curve, Jt, t from 0, 1, in the same sense. You take the space of curves, or continuous curves, in the space of structures. This is again a Banach manifold. And for the second category set of these curves, manifolds V, A, J0 and W, A, J1 are cobordant. Cobordant means that union of they form a boundary of a manifold of dimension +1. Okay. Now well, now one should always remember with these theorems that a non-empty manifold can be cobordant to an empty manifold. So the typical situation is this. Suppose this is a curve of structures. Here you have two structures, two curves, I'm sorry, C1 and C2. So this is your moduli space for structure J0. And then you have nothing for J1, and the cobordism is this. This is a cobordism between this manifold and this manifold. So the fact that you have curves for some specific structure, usually some very simple structure, gives you curves. But you want to have curves for all structures, but it does not give you curves for all structures unless some specific information you have here. Okay, now let us see what information do we have in our case. So now what we do have is the following. So we do have in general, so if I have a moduli space of parameterized curves before factoring, then I can multiply this by P1, and I have the following evaluation map from this space to my manifold X. I can take, well, U is a map from the sphere to my manifold. So I can take evaluation of phi x, no, ux, I'm sorry, to be u of x. So I take a curve and I see where this curve goes. Now I can factor this thing by action of my group, which I have. By J, and I see that if that action here, which is this, phi on ux is u of phi minus 1 phi of x, it leaves evaluation map invariant. So I can factor. So now what letters are used? I'm afraid that I already use some letter. So I use letter W and I use letter M, which is not good. Now this is M, and so I illegally changed to W. Now this is a moduli space of curves. I should not change it. Okay, so moduli space of curves, everything is good now. Well, I'm sorry for that. Please correct this. This is M. This is a space of J holomorphic spheres in the homology class A. Okay, and now here I have the universal family, and what I want to do, I want to call this factor by this letter which I had. It's a universal family factored by reparameterization. And as I explained, evaluation map now is correctly defined on this. This is invariant under reparameterization, so it's a geometric object. And since we multiplied by something of dimension 2, we have that the dimension of Waj for general J in the sense, general J in the sense of category, is our index, but plus 2, because we multiplied it by dimension 2. So index plus 2 will be 2 times C1 of x evaluated on A plus n minus 2. This is dimension J. And now let us go back to our example. X is S2 times torus. Omega is this structure, which is omega 1 plus omega 2. And now our class is a sphere times point. Now C1 of A. What is C1 of A? C1 of x evaluated on A. Well, again, what we have? We have sphere multiplied by some manifold. So normal bundle, since this is a product, normal bundle is trivial. So C1 of the normal is 0. C1 of the tangent for the sphere is the Euler characteristic is 2. The whole C1 is a C1 of the tangent, C1 of the tangent, plus C1 of the normal, which is 0, and this is 2. So this is 2. And therefore index can be calculated, but for us, this is important. The dimension of generic space of curves, the dimension of the generic space of curves is, so here we have 2 minus 2 is 2n. So for generic J, the space of J holomorphic curves on our manifold, the universal family, so curves together with this space, has dimension 2n, which is the dimension of our manifold. So we have big chances that this guy and after evaluation map will cover the whole manifold because they have at least the same dimension. So already we have a lot of curves. And the final observation, we justify this because I told you that one should be careful with cobordisms. But now we have moreover, we have a special structure, standard structure on our manifold. Yes, which is the sum of the structure on the sphere on P1 plus the structure on the torus. And for this structure, the manifold of curves in our homology class is obvious. In this case, the manifold moduli space in our homology class, which is a sphere times point and structure standard. But these are just spheres times points where P runs over the torus. These are our J holomorphic curves. So it's 2n minus 2 real dimensional family, and altogether they swap 2n dimensional manifold. And moreover, evaluation map, in this case, evaluation map from the corresponding W, so W is roughly this guy times sphere, more or less. Okay? So in this case, the evaluation map has degree 1. The evaluation map has degree 1 because it is a diffeomorphism. It's an obvious diffeomorphism. So this guy to our X is diffeomorphism. So this is a special feature of the problem because degree is invariant under the cobordisms. And since degree is invariant under cobordisms, we got that for general J, evaluation map of W, our class J to X has degree 1. That means it is surjective, at least for generic J. It is, but it's still not sufficient for us because our structure was not generic at all. So we produced some very specific structure. We took an image of the standard structure under diffeomorphism and then we extended it. So, but now if I have my manifold X and I have this specific structure, then I can find a sequence of generic curves converging to my generic structures converging to my structure in C1 alpha sense. I fix a point which was image of 0. Now for every Jn, I know that the Jn complex curves cover the whole manifold. So I can find Cn which contains this given point and which is Jn complex. And they are all in homology class which is fixed forever. And therefore areas of these curves are integrals of a symplectic form over Cn, and this is constant because this is the integral over the same homology class. So we are in Gromov compacted setting, so limit will give us a curve. Well, in this case, this curve does not, there is no bubbling, but we don't care even if there is a bubbling. Anyway, we will at the limit there will be a curve passing through 0, through this point. So once more, the general idea of Gromov's theory is that you need curves. Having curves, you can prove a lot of things. To have curves, you observe that for some specific structure, you obviously have many curves. And then you develop all this technique to prove that, and then for all structures you have curves by these considerations. Well, I will end up with another application of these ideas. Which we did in our joint papers with Shevchishin. So, who is my former PhD student. And this is a third item of my today's lecture. It will be envelopes of meromorphy. Of spheres. So the original question was posed to us by Vitushkin long ago, and question is connected with Jacobian conjecture, but I don't have time to explain you how this is related to the Jacobian conjecture. And the question is this. You take as a manifold P2. I will work only in the most simple case now. I will not, maybe I will state the general theorem, but I will prove only the simplest case. So you are in P2. Then P2 contains P1 as a line in infinity. So actually P2 is C2 plus P1. So this is a line in infinity. Now, if you have a function which is holomorphic in the neighborhood of this P1, then it means that this function is holomorphic in the complement to the big ball. By Hartog's extension theorem, this function extends holomorphically onto P2, and that means that this function is constant. If you had a meromorphic function, if f is meromorphic in a neighborhood of this P1, then by the Levy theorem it will extend to a meromorphic function on P2, and therefore it will be rational. Okay, the question was, if you take, so in an attempt to prove Jacobian conjecture, the people arrived to the point that they need to consider a perturbation of this P1. So take a sphere which is in some topologically close, or in C1 sense close to P1, but which is not complex. And then also you forget about P1, and you take a sphere. And question is, can you construct non-constant holomorphic functions in the neighborhood of such a sphere? If you can, it would be a counterexample to Jacobian conjecture. Well, you can't, but it does not solve conjecture. So why it can't? Now I'm going to explain you why you don't have holomorphic functions. Now, since S is a perturbation of P1, therefore S is symplectic. Now let me state the theorem. Let S be a symplectic sphere in a projective surface X, and let U be some neighborhood of this symplectic sphere. So I consider embedded case, but you can also consider spheres having positive self-intersections. Suppose that the value of the first chain class of your surface on S is positive. Then the envelope of meromorphy, the maximal open set over X, where all meromorphic functions from U extend, contains a rational curve. So rational curve. And what is important is that the Chern class on this rational curve is still positive. So, in our case, the Chern class on S is the Chern class on S is the same as the Chern class on P1. So the Chern class of P2 on P1, which is 3. So this is positive. And therefore, whatever neighborhood is, and whatever meromorphic function you have, it extends, in fact, onto the envelope of meromorphy, which forced to contain a rational curve. And since this rational curve in this case can be only P1, so you will extend from this small neighborhood to a neighborhood of P1, and that means to the onto the whole P2. So you are done. So all questions are clear now. So now what is the proof? What is the proof? Well, the proof, Gromov squeezing, we started with proposition 1 on my previous lecture. This proof you shall start with proposition 3. So, proof by proposition 3 of the yesterday's lecture, for a given u, I can find, so this I can find a relatively compact u1 in u, which still contains my sphere, and I can find a perturbation of structures which are all calibrated by the Fubini-Studi form on P2. This is a standard symplectic form on P2. And such that, first, J0 is a standard complex structure on P2. All perturbation takes place only in U1. So the set of X such that Jt of X is not the standard structure is contained in U1 for any t. So if you have this sphere, so then we find a neighborhood of it such that every perturbation is not trivial only here. Outside, nothing changes. Outside, structures stay integrable and standard. And at the end, we arrive to J1 such that S is J1 complex. So we make sphere complex. But structure is not integrable. And now we play back. This is the first step. Step 2. Now, step 2 is a Gromov theory. So you do what you do in non-squeezing case. You follow perturbation of structures by perturbation of curves. You construct a family, ST. Now, this is more subtle than in non-squeezing case because your perturbation is not generic. I explained you that more small and so on, they give you, well, not perturbation, they give you cobordisms, but for generic passes. Our pass is not generic because we don't allow structure to change outside of the prescribed set. And also we want more, we want not only cobordism, but we want really to follow perturbation of structure by perturbation of curves. Well, this is possible. You make more efforts. So there is a family of JT complex spheres. Well, such that S1 is S. Now we go back. S1 is X, which is the well-one complex. Well, and that's it. And then we end up with S0, which is J0 complex. And since J0 is a standard class, J0 is a Fubini-Studi. Fubini-Studi is a form. Standard structure on P2. So we get a rational curve. So this is a rational curve. Now, the third step, well, now we need to prove that this curve, which we got in the process of deformation, stays in the envelope of U, of meromorphic. That means that you can, given a meromorphic function in U, you must extend this along this family of curves and to get a meromorphic function in the neighborhood of the final curve. And then you are done. So now, what is going on here? So this is our curve. This is our S1. And now it starts to deform. it deforms. And if it stays inside of U, then you have nothing to prove. Then the limit will stay in U. But if it goes out, then it goes out by a piece of a complex curve, usual complex curve, because structures outside of the neighborhood are standard. So you are in on the assumption of the continuity principle. You have a family of complex curves, which first is inside of the domain, and boundaries always stays inside and something goes out. So why boundaries always stay inside? This is by homological reasons. S1 always intersects all ST because they are not trivial in homology. So by the homological reasons, you never leave completely this domain. So this sphere, which is ST, it's like Z, and it can go out also here, but it must cut S1. And everywhere when it comes out by pieces of complex curves. And you use continuity principle for meromorphic functions, and you extend your function along these perturbations. And therefore you end up that your function is meromorphic in a neighborhood of the final curve, S0. This is the proof. Now let me make a few final remarks. So, well, in the case of P2, in the case of original setting of the question Vitushkin, result is more negative than positive, so you don't have any functions and so on. But in general, the statement gives you much more. So, and the point is that in the statement of theorem, the resulting curve is sufficiently positive. So now suppose that this curve, which lives in the envelope, is smooth. In the envelope is smooth. You can often prove this. Then you have following cases. So you can completely understand what is going on. So the first case is whether Chern class is minimal possible. So minimal possible is 1 to be positive, yes? What does it mean that you have a curve with first Chern class equal to 1? Well, as I did several times, Chern class is sum of the Chern class of the normal bundle plus Chern class of the tangent bundle, which is 2. It's Euler characteristic. So 2 plus Chern of the normal is 1. Therefore, Chern of the normal bundle is minus 1. That means that your curve is an exceptional of first kind. You can contract it to a point. So C is contractible. Well, this gives you a funny statement, which is new, in my opinion, which was new at the point we proved this. So if you blow up a point in C2, you blow up origin in C2, you get an exceptional curve of the first kind. And then you move it. You make a perturbation, and you take a sphere, which is perturbation of your curve. Then the statement is that every function holomorphic in the neighborhood of this sphere is holomorphic in the neighborhood of C. Okay. Second case. C1 of x on C is equal to 2. Then, by the same computation, C1 of the normal bundle is 0. So normal bundle is trivial. And therefore, it is known that in this case, a neighborhood of this curve can be foliated by a rational curve. And this implies in its turn then x can be blown down. So you blow down a few curves to a ruled surface. So surface which admits a ruling over some Riemann surface with fibers which are rational curves. So you can specify the structure of X. So in the last case, if C1 of X on C is bigger or equal than 3, then you can prove that X is either P2 or a Hirzebruch surface. And moreover, since the normal bundle in this case should be positive, the curve has a fundamental system of strictly pseudo-concave neighborhoods. And therefore, if you succeeded to extend your meromorphic function to a neighborhood of such a curve, then you extend it on X, on the whole X. So the envelope of meromorph is the whole X. All meromorphic functions which were defined in the neighborhood of our symplectic sphere are in fact rational. Which was the case with initial case with P2. Okay, that's all. Thank you.